So hello everyone, and thank you so much for attending my talk. So I am Dorra, and I'm from ENAC. It's the French National School of Civil Aviation. And today I will be presenting our paper towards bit-level dominance, preserving quantization of numerical classifiers. So this work is in collaboration with Matthieu Martel from University of Peprignan in France. So, as we all know, GNNs nowadays are massively over-parameterized. So, for example, if you take models like GPT-3 with more than 1,075 billions of parameters, we have also models like Matthieu with more than 70 billions of parameters. So these huge numbers of parameters make such models hard to deploy on real-world embedded systems, especially that these systems have some limited resources. So here we talk about resources in energy, in memory, and bandwidth, etc. So let's take a concrete example of the model Matthieu. So the Matthieu with 70 billions of parameters have been trained on 6,000 NVIDIA GPUs running non-stop for 12 days to make the computations. So this takes 1.7 million GPU hours to fine-tune these models. And the output of this model was compressed, and the final file is of 140 gigabytes. So why I'm giving these numbers and giving this discussion is that to show that it's true that such models are huge and are complex, but sometimes we do not all need all this complexity and this is why there are some models or some new techniques for doing reduction and optimization. So there is a need to do some optimization, but the key question is what can be reduced? So many optimization techniques are available and are in the state of the art. For instance, we can reduce the number of weights of these models. Techniques like pruning and like knowledge distillations are available for this. The second kind of reduction technique, and which interests us the most in this talk, is the quantization. So when you take quantization, you want to reduce the precision of neural networks. So how low can we go? So when we reduce the precision, either we reduce the floating point precision for which the neural network has been trained. For example, we move to 16 bits or 32 bits, so for reasons for speed and scale. The second one is to do some mixed precision, which means that some neurons or some precision will be in 16 bits, the other one 32 bits. So we merge several types of precisions in order to give a good trade-off between performance and accuracy. There is also another type of quantization is to change the arithmetic, is to convert from floating point arithmetic and to go to fixed point arithmetic, which is based on integers. So in this work, we are only interested in doing quantizations, but by keeping the floating point arithmetic for the quantized neural networks. But once we have done the quantization, what should we quantize when we do such quantization? So generally, or in the literature, the state-of-the-art models that do the quantizations are doing quantization based on error guarantee they do it that they give on the output model. So what they do, they take the floating point neural network and they go to give on the output an error guarantee, for example, that the error bound between the original floating point neural network and the quantized one must be less than a small error, which is here epsilon. So tools like Aster and previous tool of ours like Poppins do this. They synthesize fixed point codes for neural networks, but based on such guarantee. So this is very good. So our outputs match original network. However, this method does not suffice, or it's not enough for doing quantization. Why? Because it's true we give guarantee on error bounds, but it's not a property or functional property that determines that the quantized neural networks behaves correctly like the original one. So, and in this talk, what we are interested in is in quantizing neural networks, but giving guarantee on a more important functional property, which is dominance. So, which is dominance in the case of neural classifiers is keeping the order of output unchanged for the quantized neural networks. For instance, we have two classes, class A and class B. So the output of class A, for example, the score of the output of class A is higher than the output score of class B. Then after quantization, with our method, we want to, in the quantized network, this score is unchanged, which means that class A is always dominant than class B. So how to do that? So this is what I will explain in this talk. So the goal is to preserve the dominance quantization of neural classifiers. So how we proceed is by determining the minimum precision required for quantization to ensure the preservation of dominance. We will perform only post-training quantization and with uniform precision. Uniform precision is to mean that we have only, for example, 16 bits or 32 bits. We will not have mixed precision at this level of work. And we will compute by this post-training quantization the minimum number of mantissa bits. So the mantissa bits is the significance of the floating point numbers. And we will compute such precision independently of the IEEE 754 formats, which means that we will give the new precision at bit level. For example, 9, 8, 18, etc. So from now, we will introduce two types of precision. The original precision, PO, we denote it, so which is the original full precision of our, for which the neural network has been trained. And what we want to compute is PR for precision reduced, which is the unknown and we want to compute by our method. So of course, the two precision are in F, and F is the set of all floating point numbers. So let's go a little bit inside the method. So how to do the dominance of neural networks. So simply we consider a neural network. The input of our neural network are x, so the vector x here with n, with size of n, and the vector x is in the original precision. We have a matrix of weight W, so the matrix of weight of size m times n. And we have Y, so Y is the output of our neural networks, which is the size of our output are m. And the neural network is doing just multiplication, so the output Y is a multiplication of x and y. So we say that a class E is dominant for some E if we have two classes, for example, E and G, so the output of the class Y is greater or equal than the output or the score of the output of class G. So this is the basic definition of the dominance. So in this work, I'm just going to talk about dense layers. I will not present activation functions, and I will focus only on single-layered, fully connected neural networks. So, as maybe you know that when we perform floating point computations, so there are errors that can occur and are introduced in each operation. So these errors are captured by what we call epsilon machine. In other words, epsilon machine is the gap between 1 and the next larger floating point number in finite precision. So why I present an epsilon machine? Because in the context of quantization of a neural network, so when we quantize or reduce precision, we will introduce errors in the neurons. So these errors that are introduced, we need to bound them with, so we bound such errors, and we will use the epsilon machine to determine how much precision that we can afford to lose without changing the predicted class. So, and then the epsilon machine is equal to 2 to the power minus p. So here, when I don't say p original or p reduced, so I'm talking with on both precisions. So following the standard model for floating point arithmetic, so here I take the input, the output, and the matrix of weights in original precision. In the quantized neural networks, we have x hat, y hat, and w hat, which are our new input, output, and matrix of weights in precision, or in PR, which is the reduced precision. So equation 3, 4, and 5 are so when we are the new, or the definition of x hat, which is x times 1 plus certain error, y, which is the matrix of weights, which is the matrix in floating point original precision times 1 plus certain error, etc., and y, which is the result of the dot product. So if we follow such these equations 2, 3, 4, and 5, so we say that the dominance is preserved if we have a quantized neural networks if the original so the original output of class I is greater or equal than the class G, then in the quantized neural networks we will keep correct this inequality. So for that, we will apply in this work the theorem of Ramp's error bound on dot product. So what tells? This theorem was published in the error estimation of floating point summation and dot product journal paper in 2012. So Ramp said that if we take n-dimensional vectors x and y in a precision, and we have the new floating point or the new x hat and y hat in a reduced precision, then the error bound of the dot product can be bounded by such quantity. So, and we will use such theorem in order to find the reduced precision that you want to compute on our quantized neural network. So let's do it. So we will follow the Ramp's logic. So we will take our classes, the output are our classes, so class E and G, and we have YE, which is the dot product WE XK, and we have the other class, the output G. We will take the same but in the absolute value, and we'll propose or define this new proposition to preserve the dominance, or the condition to preserve the dominance. So following Ramp, so the dominance of class is preserved if our epsilon machine, which is the error bound of the quantization of our neural network, is less and equal than this quantity. So the full proof of this proposition was provided in the paper, and this orange inequality guarantees that after the quantization that we did with our method, the predicted dominant class remains unchanged. So, as our goal is to minimize the precision PR or P-reduced while preserving the dominant class, we found that we are in face of a nonlinear optimization problem. So this huge inequality is the problem that you want to minimize. So what we have as known or unknown parameters. So what we know is n, which is the input vector dimension. We know the weights of our neurons. We have also xk, which are the elements of the input vector belonging to range between 0 and 1. So all these are known before before solving our problem. And what is unknown is the PR or the reduction precision that you want to compute by our methods, and which is given by some epsilon machine u is equal to 2 to the power minus PR. So to solve this problem, so we in face of a nonlinear constraint to find the smallest PR that guarantee the dominance. So to solve this, so we need to find, to maximize the epsilon machine in order to find the smallest PR possible for which the quantization guarantees the dominance of our classifiers. For that, we will use the optimization method known for the large-scale problems, which is the trust region constraint algorithm. So, which is based on an anterior point algorithm to solve large-scale nonlinear programming. So we have tested only this optimization technique. We do not test another solver, maybe in future work. So after solving this equation, so we move to the experimental results. So what we have in the experimental setup is the datasets and networks. So we take the MNIST dataset for handwritten digits, the diabetes for the medical features, the CIFAR-10, which is dataset for RGB images, the cards, which is a dataset for playing cards, the rice for rice varieties, and waste, a dataset for recyclable waste images. And here we show the input shape of the dense layer that you want to quantize. So we quantize only the dense layers as we said, and only single layer per neural network for now. So what we need to take in consideration is that all inputs for our models are normalized between 0 and 1, and that the quantization is applied to only the less dense layer, but except for diabetes and weights, which is the penultimate layer, because the last layer is used to calculate or to compute the score. So let's move to the first results. So in this table, what you want to do is to compute the reduced precision PR and to also to show the saved memory that we obtain when doing this quantization. So initially, all our neural networks have been trained in original precision, which is the single precision with 23 bits of mantissa. We take here, we display all our networks, the layer shape of the dense layer. So what we can see is that when we solve our optimization problem, we found that the reduced precision ranges between 9 and 15 for our neural networks, starting with initially with 23 bits. And we have a saving memories falling between 34.7 to more than 60%. So for instance, if I take the MNIST example, so for the MNIST example, so we found that the reduced precision is equal to 9 bits. So, and we can save more than 60% of memory, and with only precision of 9 bits, we keep the dominance, and we cannot violate the dominance of our neural network. So the second experiment investigates the scalability of the method. So here what you want to take is the case of the MNIST dataset, and we will vary the classes. So we'll take, for example, a class 3 and class 5, and also we will vary the image sizes going to 5 times 5 to 28 times 28 images. So what we have here on your left-hand side is the plot of the reduced precision versus the input size. So in the x-axis, here we have the input size of our MNIST model, and in the y-axis, we have the reduced precision PR computed by our methods. And the green plot is for class the class m equal to 3, and here for the output equal to 5, the blue one. So what we can see or observe in this plot is that we have imported gain in a reduced precision. For example, here for 10 by 10 image input size, we have 6 bits of precision reduced, etc. And also in time of execution time, on your right-hand side, we found that our method for all or across all networks is fast. So if we can find the new precision needed for the quantization in only a few minutes. So let us now discuss a little bit limitations and what we need to do in future work. So as you have said, our work is limited to only dense layers, and for now we don't address the composition of multiple layers, neither for activation functions. So what are the directions that we want to take to address the most common layer types in your classifiers? So for activation functions, so most activation functions, the ReLU, the sigmoid, etc., are monotone. So we said that perhaps if we do not change, such activation functions do not change the dominance, and they can be ignored during the quantization process. Concerning the monotonic layers like max pool, min pool, upsampling layers, etc., also they can be left as they are in the quantized network. For the convolutional layers, so the convolutional layer, it performs a sequence of operation of this form. So generally, this form, we have a sequence of multiplications and additions. And we believe that they can be performed in the same way like we did in dense layers. And I finish with the multi-layer networks. So when we have multi-layer networks, this is the real problem, because it's a composition of the composition of monotone functions is monotone, and this should help in solving the problem. But for now, we didn't proceed to do the composition of such multi-layer networks. So the take-home messages. So I presented a novel quantization method that preserves dominant class for classifiers. Our method does not rely on score approximations, but it ensures the predicted class remains unchanged. We are based on a theorem of ramp in order to bound the errors to formulate a nonlinear optimization problems. And the first experiments confirm that our method is practical for the data sets used. So perspectives, we want, as I said, to extend to more general neural networks. Why not to combine with other optimization techniques like pruning and knowledge distillations, and to explore other alternative solvers and relax constraints for speed. So that's it. Thank you for your attention.
Yeah, because of this time limit, so we should have discussion offline, a Q&A session offline. So thank you.
Thank you.